Let us get started. Christine Berkesch is back to give the second lecture for multigraded modules.
All right, thank you, Fred. Can you hear me okay? Is this working? Okay. So, multigraded modules. I wanted to give you some motivation last time, and so I told you a lot of geometry. Now we're going to shift into more multigraded mode with that geometry in mind. Okay, so just to remember, right, I told you that there are these things called simplicial torque varieties. They hand us polynomial rings. These are the Cox rings. I realized I didn't actually say that. It was in the exercises, right? So this is called the Cox ring. In the book, David Cox insisted this be called the total coordinate ring, but we all call them Cox rings. So this Cox ring is just a polynomial ring with that has a z to the r grading, we'll say, that's given to us in this way. And along with that is this data of this irrelevant ideal. And there are no points in our variety that correspond to this. So like this geometrically is irrelevant. That's why it's called the irrelevant ideal. And this is a monomial ideal, which turns out to be quite useful because we have lots of tools for monomial ideals. And so when we're constructing this variety, we start with our big affine space and we throw away all the points that are zero for this ideal. That's why we call it the irrelevant ideal. And so if we're trying now, I told you there's the story of the geometry of syzygies for projective space, that we can take minimal free resolutions over a standard graded polynomial ring and extract all this geometry from them. We would like to be able to do that in other settings, in particular things like this. And today we're really going to focus on products of projective spaces, which fall into this world. So they're kind of the next step past projective space to dip our toes into the water here. But already there's complications. And so the thing that it turns out is useful to look at are these things called virtual resolutions. And the idea is we're going to allow ourselves, instead of kernel equals image at each stage as we compute free resolutions, we allow ourselves enough space to have homology supported on B. So our homology has to be annihilated by a power of B. Okay, so let's do an example. So this is the one from, I think, number 4 on your exercises, the first exercise set. So I have P1 cross P1. Remember, C is our algebraically closed field. Okay, so the degrees on these variables we'll say is 1, 0, and the degrees here are 0, 1. Oh, and I'm going to push this up. So, okay, so these are our degrees. And I want to look at, inside of here, 2 points that have this ideal. And I should contrast this with my irrelevant ideal here. So here I need the origins that came from the 2 affine spaces. So I'm taking the x variables intersecting with the y variables. So in terms of projective space here, this is kind of like 0, 0 and infinity, infinity in my product. Okay? So if you go into Macaulay 2, give it this ideal, ask for the minimal free resolution. This is what you get. All right, let's look at this. So I'll abbreviate MFR, minimal free resolution for S mod IY. Right, so I have 4 generators for my ideal, right? I have my x0, x1, that's 2 x's and no y's, so that gets a 2, 0. And then I have the 2 mixed terms. I have x0, y1 and y0, x1. Those are both 1, 1, so there's 2 of those. And then I have 2 y's. That's this. Okay? And then as I start going back, this turns out to be a 1, 4, 4, 1 resolution in terms of total Betty numbers. And this is what it is, right? So minimal free resolution, right? 2-dimensional space. length 3. So as far as Hilbert syzygy theorem goes, we're already in trouble, right? But let's just introduce some B torsion here, right? Let's do instead, I'm going to write it here so you can actually see it. Let's do the minimal free resolution now of S mod IY intersected with B, right? So geometrically, this is doing the same thing. Okay, so this is what we're resolving. So I now have an S. If I intersect with B, I'm forcing myself to have terms that always have one X and one Y, right? So in terms of my generators here, these two are not allowed. I'm keeping these two. So this becomes this. Okay, so I now have two things here I want to resolve. Hopefully you're now excited because this is the best of all complexes, right? This is just a Kazul complex. I have two terms here and I flip them with one negative sign. I now have this just the Kazul complex on these two forms, and that's it. All right, so I went from this huge thing to a different complex that's still actually acyclic, but geometrically is doing the same thing, but now it's short, and it's in fact just a very nice Kazul complex. Right, so this is the idea in this geometry of syzygies. We're playing this game where we're like throwing in a little bit more homology, and in the process getting some nicer complexes. And the hope is to pull more geometry out of those nicer complexes. Right, we're paying a price. Remember, minimal free resolutions are unique. These are not unique, right? We're going to see two more virtual resolutions for this, this Y, this S mod IY later. Okay, so we're losing uniqueness, but that's okay, right? Like with this multi-graded thing, like things are happening in many directions. So like maybe we shouldn't have expected uniqueness to begin with. Okay, all right. So we're going to talk more about the Hilbert syzygy theorem tomorrow. Right, that'll be the point of tomorrow, is to kind of resolve that problem, because that one is resolved in this general setting. But today I want to talk about regularity. Okay, so I cheated and I gave you a recall. So last week, Claudia did me the great service of teaching you about Castanova-Mumford regularity, and she gave you 3 different definitions. Right, so now I just, to try to distinguish, if I just work over a projective space, I called it PM, so we have a different letter, and I used R for my standard graded polynomial ring. If I choose an ideal I and I look at its regularity, or a module for that matter, you could substitute through. I can do it 3 different ways. I can look at the Betty table and see how many rows it has. Right, this is numbers of rows of Betty tables here. Right, that one's really nice because it's fast and easy and like visually pleasing. Right, I can look at truncating. I can just take R mod I, cut off the degrees below L, right? And the minimum L, where I get a linear resolution for that truncated module, is another way to compute regularity. And this one has a name. So the fact that these are equivalent is the Eisenbud-Godot linearity theorem. That's what we'll call it today. Okay. And the last one is worse to some. I think it's beautiful, but if you don't know local cohomology, that's okay. Take this on as like an incentive to say, oh, maybe I should go learn that when I get home. All right, it's going to come up more. So here we're looking at these local cohomology modules supported at the graded maximal ideal, and looking at non-zero degrees there. Right, and that's another way. All right, if you haven't seen this before, this is actually very closely related to sheaf cohomology. So geometrically, this is like doing something geometrically, and that's where Mumford was motivated to start. And then we got lucky that we could read it off of syzygies. Okay. So now we're back in our multigraded setting. Now I have vectors, even for P1 cross P1, I have vectors in Z2. What does linear mean anymore? Right? Like, I mean, here it made sense because I was in the integers and I'm just like moving along one by one. But like once I'm in like a plane of lattice points, like, am I just marching in one direction? Am I thinking about the variables? Like we have options, and that creates some problems. And in particular, like these kinds of equalities completely break down because they don't even necessarily make sense. All right, so Diane McLagan and Greg Smith gave us a place to start. And they said, let's look at the last one because we know that's telling us about geometry. Okay, so this definition we're getting closer to the present day. Okay. So in 2005, he said, let's take a vector now in Z to the R. And let's assume, just to make this definition easier, right, there is a version without it, but it's worse. Let's assume now that I'm starting with an ideal where this local cohomology module is 0. Okay, that just means this doesn't have any B torsion, or B is not an associated, no components of B are associated primes. Okay, that's all we're saying. All right, so we'll say then that we're deregular if, all right, this is terrible and you don't need to like process this at all. Okay. I'm taking every vector in the degree set of S. All right, we're going to kind of step one step back. That's it, okay? Don't try to internalize what this is. It's okay, you don't need to understand it at all for moving forward, right? The thing I want you to take away is this is the correct analog in this multigraded setting of this last one, right? That's all you need. All right, and so now I should give you some examples, right? Because what does this mean? All right, so in our example here, I can fit it in. So our P1 cross P1 that we have running, the regularity, oh, I should say one more thing before I do the example. Let me give you the notation. So regularity of S mod I is going to be the D's in Z to the R, where S mod I is deregular. Okay, so just the collection. So if up here regularity was just a number, right, an integer, but once you were regular at that integer, you were regular like at every one past that, you had like this linear resolution property. So you could think of regularity for projective space instead of being an integer as being like an array inside of the integers, like you have some cutoff and you take the interval from there to infinity. So here that's kind of what we're doing, is we're going to have some like corners and we're going to take everything kind of above it with respect to the degree set of S. Okay, so this in particular now is some subset here that's closed under addition by the degree set of S. Okay. All right, so now examples. So our Y, 2 points inside of P1 cross P1. that we had has regularity like this. Right, so the degree set of S is just the orthant. Right, there's no way to know this without like doing a bunch of computations, right? So this is, I'm giving you some of these so you can like see what they look like. And this should feel mysterious, and that's okay for right now. Yes. Oh, thank you, yes. And in fact, there is Macaulay 2 code to compute this, thanks to Mahrid, who is around. So let's draw this picture. I'll draw it up here. So I have my orthant, and now I'm looking at 1, 0, and 0, 1, and I can add to that any lattice point in n to the r. So I'm looking at this intersected with Z2 is this regularity of S mod IY. Okay, that's not so bad. All right, another example. I cheated a lot ahead of time because these are terrible. So there is a curve that I picked. It happens to be hyperelliptic, whatever. It's defined by these 8 equations of various degrees. This is the curve from one of the exercises inside of P1 cross P2. It has this kind of massive resolution, right? Massive as far as writing things on the board goes. Maybe not massive for Macaulay 2, but that's okay. All right, so this is this curve, and I'm going to tell you what the regularity of that is, and I'll write it down here. All right, so here I have, let's see, 2, 2. I have 4, 1. So this is 4, 1. The numbers aren't so important. And again, Macaulay 2 will do this for you. And is it 1, 5? Right, so we're intersecting, of course, with the integers. Okay. So this happens to be the regularity for this thing. All right. If you look at this, right, like remember over here for projective space, we could see the regularity from the Betty table. Like I look at this, I have seen no indication that I should know that these are special with respect to this free resolution. I don't know, how about you? You see those numbers? All right, so Mark Chardin and some of his students have worked very hard to try to extract some of that, and they actually have some nice results that are complicated, because this whole thing is complicated, but you can see a little bit, but it's tough, okay? It's certainly not this nice Betty table type thing. Okay. Got it. Where did my white chalk go? Yes.
So M2, now there's M2 stuff for not only the regularity, but also these, I'm sure these multi-graded resolutions do that.
In terms of?
And there's M2 code for both of them.
Oh, yes, yeah, and I will give you, at the end, I'll tell you the packages you need for the exercises. Because you're gonna need more packages too, but I haven't told you what you need for those yet. All right, I'm gonna leave this example. I'm gonna give you a theorem. I think. All right, so one thing that we can do is relate virtual resolutions to regularity, and in fact, use regularity to get virtual resolutions. Okay, so this is for products of projective spaces. Now we're at 2019. Okay, so kind of the rest of the talk. The results we're going to see are for a product of projective spaces like this. I guess there's this result and one more. All right, so I choose some y inside of my x, a subvariety, and I have d in the regularity of S mod IY. And then I need the minimal free resolution of S mod IY. Okay. Then the subcomplex of F with some ands. So I'm going to throw away part of this F, but I'm going to tell you the part I'll keep. So I'm going to keep the parts generated in degrees less than or equal to d plus n, where here n is my vector n1, n2 out to nr. This is a virtual resolution. Okay. Yes. Yeah. So I'll show you. I'm going to go through each, right? So everything is like S twisted by something, and I'm only going to keep the ones where the something compares nicely here with the sign. Yeah. Oh, yes. Yeah. This is component-wise comparison. Sorry about that. Yeah. Okay. So here, right, if I'm using, right, I told you 1, 0 was in the regularity for my 2 points over at the top of that board over there. So I'm going to look at 1, 0 plus 1, 1, because I'm in P1 cross P1. So I have 2, 1. So now I go through and I see a 0, 0 here. That's, 0 is less than or equal to 2 and 0 is less than or equal to 1. So this stays. Now I'm ignoring signs. So I'm going to compare 2 because this is like the twist and the degree of the generator is the negative of that. So if I look at 2, 0, 2 is less than or equal to 2, 0 is less than or equal to 1. So this stays. 1, 1, also good. 0, 2, this is a 2. That's a problem, right? Because the 2 is not less than or equal to 1. So this one goes. So now I'm going to go like this. And it turns out this is what I want. All right, so here, right, the 2 is bad here, 2 is bad there. Okay, so this is also a virtual resolution for S mod IY, and it's a subcomplex of the free resolution. So, maybe regularity is reflected in a different way inside of these minimal free resolution. Similarly, right, this is totally symmetric and everything. So I can do the same thing the other direction. I get this, right? So now you have 3 different virtual resolutions besides the minimal free resolution for S mod IY in this example. All right, so that's that. And then I wanted to do one for the curve as well. So over here, let's use this 4, 1. Okay, so if I do 4, 1 plus now 1, 2. I have 5, 3. Okay, so now this is a pain. So I'm just going to tell you what stays. Very little stays. In fact, it is, wait now. Let me check something. Yeah. Okay, I'm good. I got worried about a betting number, but it was right. Okay, it's this. This is what stays. So you can check that later. Okay, this is now total betting numbers. 1, 1, 2, 3, 4, 3. So we went from like this horrific thing to actually a Hilbert-Birch resolution, right? So one of these, like these equations now are minors of this matrix. Kind of cool, right? Way smaller, way nicer. Hope you're like, yeah, I'd much rather deal with this than this big thing, right? It's actually really awesome. This resolution, the existence of this resolution, there are other theorems in geometry that tell us about the deformation theory of this curve, telling us that it's unobstructed in its Hilbert scheme because it has this nice resolution geometrically, which is something the minimal Fourier resolution didn't have, right? So this is, I say that to tell you there's a big story here, right? That like finding these nice complexes tells us cool things. All right, so there's one more thing I want to tell you about, and that is this, right? So what the heck should linear be in this setting? And I'm going to tell you the answer by pictures, right? So the Kazul complex on the variables is linear for projective space, right? Great. So you could hope that in this world, in this multigraded world, we could use the Kazul complex on the variables again. But that kind of corresponds to the maximal ideal, right? That's not what we want. We want the irrelevant ideal. Okay, so I'm going to draw a picture. Instead of writing down a formal definition. All right, well, first, let's see. So let's actually do the Kazul complex first, just because that then you can understand the picture. Kazul complex on the variables for P1 cross P1. Okay, what do I have? I have two X's. I have two Y's. And this is actually a Kazul complex like on the variables separately because the X's and Y's don't interact in the grading. So it's like two Kazul complexes put together. And so here I just have this. Okay, so here's the picture. I'm going to actually use the negatives this time. So 0, 0 is a generator in homological degree 0. So I'm going to write it there. Right? In homological degree 1, so here's the 0. Here's homological degree 1. I have -1, 0, and 0, -1, which is a little harder to see. Okay? And then last, in homological degree 2, I have, oh, did I do this right? No, I think I did this wrong. Sorry, looking in the wrong place. This should be this, 3. There we go. Okay, the Betty numbers don't matter here. All right, there we go. And then I should have a 2 here, okay? Oh, it's better. All right, so this is a picture I can draw. Right, so if I were looking just in a single projective space, this would look like linear and these would have collapsed because I'd be summing along these, but I'm not. Okay, so for S mod B instead, this is the picture I get for P1 cross P1 and for any two products of projective spaces. In fact, it is 0. And remember, everything here has mixed terms of degree -1, -1. So now this is here, and then it kind of branches out. So I get -2, -1, and -1, -2 in the next homological degree, and then 3s. Like in homological degree 3, those 3 degrees appear with some multiplicity. All right. So I'll write down the last results and then be done. Well, I'll tell you what packages you need first. Okay. So this is now a virtual Eisenbud-Godel linearity. Oh, and I forgot the year. Actually, don't think it's appeared yet. Let me tell you. Wait, right, so this is Juliet Bruce, Lauren Cranton Heller, who I think will be here tomorrow, and Marid Sairafi, who's already here and been helping you with exercises. All right. So I'm taking something, again, inside of my product of projective spaces. And I want to say D is in the regularity for Y. This works for modules too, I should say. All right, so I'm going to truncate here. I need to explain what this means. All right, so keep the degrees in D plus n to the R, right? I have an orthent. I slide it to D and I keep everything in here now that sits above that. So it's like a component-wise comparison. So this has a quasi-linear minimal free resolution. And I need to tell you what this means. I'll do it. I'm going to leave this up and I'm going to write it here where there's more space. And I have this. All right, so quasi-linear. What I want to do is I'm going to shift this diagram so that 0 lives at minus D. So shift this to minus D and look at where Betty numbers occur. Okay, so if this were like a linear thing, it would just be a line and you'd be sliding your line to make sure the Betty numbers fall in that little segment. Here now, if we were just looking at truncating here, we would want our 0th Betty numbers to live here. And then we would want our homological degree 1 Betty numbers, our first Betty numbers, to live inside that region. Our second ones to live in here. Third ones to live in here. So that the resolution, the minimal free resolution of S mod B is governing what linearity should be for a theorem that tells you how to think about regularity in terms of truncations. Okay. So I know I'm way over. So let me just write down 3 packages. So there is a virtual resolutions package, right? And to find things like this, that's called virtual of a pair. There is, and before that, you need normal toric varieties. That's the one that lets you define Cox rings. And then last, the truncations package will let you compute the minimal free resolutions for truncations. So you don't want to do that by hand. Okay? All right, thank you so much.